Welcome to the third integration lesson, integration 3. Today we'll be learning how to integrate the trig functions, and we'll learn a new technique called integrating by substitution. Just to recap where you've come from, remember you've learned now the power rule, the constant rule, the constant multiple rule, and also sum and difference rule. And then last day, in the last lesson, you also learned the rules for integrating the functions e to the x, and ln x, or I guess the integral of 1 over x, which is ln x. And you also learned how to deal with a linear argument, how to integrate with a linear argument. Today, like I said already, we're going to learn how to integrate the trig functions, and we're going to learn a new integration technique called substitution. Alright, so first of all, the integrals of the trigonometric functions. Again, the same pattern as we've already been dealing with. It's the reverse process of differentiation. So the integral of sine x is negative cos x. That's the only tricky one to remember. And the integral of cos x is sine x. And then what we'll do is we'll combine that with the rules, or the dealing with the linear argument that we learned last lesson. Whereas now the integral of sine is still negative cos, you'll notice. Notice how the argument stays the same, but we have to divide or multiply by the 1 over the coefficient of x. Alright? So that's the negative 1 over a, or the 1 over a term. The negative is part of the integral of sine. Same thing with integral of cosine of ax plus b. Again, the integral of cos is sine. And the argument stays the same, ax plus b, but because that argument is linear, we have to also multiply by 1 over the coefficient of x. Alright? So again, as you've been seeing now, with all of the types of integrals that we've done, and now we've dealt with all of them, we've been looking at all of these with a linear argument. In the brackets, we have an expression that's in the form ax plus b. And the pattern has always been you would integrate the function as usual, as you would normally. You keep the argument the same, but you have to remember to multiply by 1 over the coefficient of x in front of the function. Alright? So just a couple of quick examples using this pattern. So the integral of 6 cos 2x minus 5. Again, if you like, you can use the constant multiple rule. You can take out the 6, and then you're just integrating the function cos 2x minus 5 dx. Again, the integral of cos now is sine, so it's going to be 6, and the integral of cos, like we said, sine 2x minus 5. But because the argument 2x minus 5 is linear, we have to multiply by 1 over the coefficient of x. And again, don't forget plus c. And then this can be simplified to 3 sine 2x minus 5 plus c. Alright. The other example here again, if you want to use the constant multiple rule, you can take out the 1/3, and then it just becomes the integral of sine 3x plus 4 dx. Again, we'll apply the integral rule for sine, which is negative. I'll put the negative right out in front. The 1/3 is the coefficient from the original question. And the integral of sine, like we said, is negative cos. Keep the argument the same, 3x plus 4. And then now we have to start adding plus c. And again, because that argument is linear, the 3x plus 4, we have to also multiply by 1 over the coefficient of x. So here the final answer now would be negative 1 over 9 cos 3x plus 4 plus c. Alright, so that's those are the sine and cosine integral rules applied with linear arguments. And again, as long as the argument is linear, you can use this pattern that we've looked at where you multiply by 1 over the coefficient of x. But it's probably likely that we won't always have integrals of that form. Very often they will be different. They won't just be a linear argument. One other style that we're going to look at, one other type of integration, it's called substitution, the substitution method. And it can be useful when you have a composite function. So that would be the f of g of x here, all right, is multiplied by the derivative of the inner, the g prime of x, all right, that's what that's showing, all right. And again, it's a unique case, but it does come up, so it's worth knowing, all right. I've simplified it to some steps here, so the example will be on the far right. The steps are on the left here. The first step, obviously, you're looking at your integral that you need to take, and if you can recognize that part of the expression is the derivative of, let's say, the internal part of this expression, then it's a good chance that substitution will work. All right. So when I'm looking at this, I can see that 6x plus 5 does look like the derivative of 3x squared plus 5x, possibly. All right. So what we're going to start with is it's called the substitution method. This is the reason. I'm going to pick the most complicated part, or the highest order, the part that has the highest exponent. And again, we're looking in the parentheses at that. So I see that 3x squared plus 5x, that's the highest order part of this expression. So I'm going to substitute that with u. All right, so I'm going to equate u to 3x squared plus 5x. All right. Once we've got that, the second step is to take the derivative of u with respect to x. So we're really taking the derivative of both sides. Using the notation, we have du by dx on the left, and the derivative with respect to x on the right is 6x plus 5. And now, doing a little bit of cross multiplication, we want to isolate du. We cross multiply, and we get the expression du is equal to 6x plus 5 dx. And you can just simply think of that as cross multiplying. The next step then is to recognize in the original expression which parts do we now have defined. All right. Well, it was obvious we chose u to be the 3x squared plus 5x. But now what we've calculated from the previous step is that du is actually equal to 6x plus 5 dx. So wherever I see 6x plus 5 dx, I can replace it with du. And so now this whole expression can be simplified down to, by replacing the 3x squared plus 5x with u, it becomes u to the 4, and replacing the 6x plus 5 dx with du, it becomes u to the 4 du. And now this is just really a simple little integration power rule question. All right. So again, we're going to follow the integral rules, the power rule for u to the 4. And again, it's add 1 to the exponent, divide by the new exponent. And so that expression now would become 1/5 u to the 5. And now don't forget your plus c as well. All right. And now, obviously, the original question is in terms of x. So we can't just leave our answer in terms of u. So all we do is we substitute back into that expression what we originally substituted u for. And u was, if you remember, it's shown up here. U is actually 3x squared plus 5x. So I can take that and put it back into u. All right. So my final answer in terms of x is the 1/5 3x squared plus 5x to the 5th plus c. All right. So that's the substitution method there. We'll have a couple opportunities here for some examples. All right. So again, like I say, usually start by trying to find the most complicated part of the expression and set that equal to u. So in the first question here, I would let u equal the exponent 4x squared plus 1. And now all we do is we take the derivative on both sides. So du by dx is equal to 8x, and cross multiply. du is equal to 8x dx. Now, if you look back in the original question, you'll see that what you really have, though, outside of the e function is you have x dx. But right now I have 8x dx. So what do I need to do to make this equivalent to x dx? Well, it should be divide by 8 on both sides. So if I divide 8 on both sides, I now get 1/8 du is equal to x dx. And now we just perform the substitution again, the same as we did before. So we have now integral. It's going to be 1/8 e to the u du. All right. And again, you can use the constant multiple rule. So this is 1/8 integral e to the u du. So now this becomes, and again, e is its own integral. So it's simply 1/8 e to the u plus c. And again, like we did last time in the first example, we need to replace the u again with what we substituted it for originally. So this should become equal to 1/8 e to the 4x squared plus 1 plus c. All right. All right, let's try the next one. Again, look for the most complicated or the highest order part of the expression. I would say that is the x squared plus 3x under the radical. So I'm going to let u equal x squared minus 3x. I'm going to kind of skip the step of making it du by dx. We know that the dx will always end up on the right side. So I'm going to just say du now is equal to 2x minus 3. Keep that together. Dx. All right, and now I can clearly see that in my original, I have a grouping that looks like 2x minus 3 dx. So I can rewrite my question now as the integral of the cubed root of u du. Again, what I might do is I might rewrite that as integral of u to the 1/3, so I can use the power rule. And now performing the integral, we have u to the 4/3. And using the power rule, remember we have to divide by the new exponent of u in this case. That we can rewrite as 3/4 u to the 4/3. We should add plus c in here. And then my final answer will be, again, substitute what we originally let u equal. So it's going to be 3/4. My expression for u was x squared minus 3x. And that would be all to the 4/3 plus c. And again, if you want to rewrite with radical, you could rewrite this as 3/4. It would be the cubed root of x squared minus 3x all to the 4 plus c. Not totally necessary to do the last step, but if you'd like to, you can do that. And now the third example on this page. Again, try and identify the most complicated or highest order part of the expression. Again, hopefully you recognize that as the denominator. All right. So we can set that equal to u. So u will equal 3x to the 4 minus x cubed. And when we take the derivative on both sides, we get du is equal to 12x cubed minus 3x squared dx. And again now, hopefully you can see this unit here is the same as this part of the expression. So we're in good shape for our substitution. So now we can say this is equal to, it's du over u, which can actually be thought of or written as 1 over u du. We can move the du to the side. And now we perform the integral. So the integral of 1 over u should be very simple. It's ln u. Don't forget plus c. All right. And now we should, again, substitute back our expression for x that we let u equal from the beginning. And that will make this ln 3x to the 4 minus x cubed plus c. So that finishes this part of the lesson. We'll complete the rest of the examples in class.